All righty. So today we get to do way too much animation, but we're going to walk you through a bunch of synchronization examples. And for those of you that were worried that you didn't know what a monitor was by the end of the last lecture, that's okay, because we didn't really tell you. So, all right. So, if you remember, just as a quick recall here, we were talking about how to make a lock out of disabling and enabling interrupts. And the important part was you can't really have acquire and release directly disable or enable because it just would tie up interrupts for too long. So instead, we use the disable and the enable interrupts as a way to design the lock, and we put the critical section in between here is actually something that's very quick, which either grants the lock or puts you to sleep. And as a result, this was an implementation that is at least plausible, but only what? On a single CPU. Okay? And what I'm going to do in a couple of slides is I'm going to walk you through how this actually works so you can see through the glorious animation of PowerPoint how this actually works. But were there any questions about this implementation before we went further? Anybody? Okay, no questions. Good. So the second thing I wanted to do was I did an on-the-fly edit last time. I don't know if you guys noticed it, and realized that the reason I was doing the on-the-fly edit was because there weren't good enough constraints in the comments, and so I wanted to make sure that I walk you through this. So this was the way to use the test and set operation, which you remember was an atomic operation that's provided by most processors that is really a form of busy waiting, but just like with the previous example, we're going to use the test and set just as a locking mechanism to put a critical section around the lock implementation that we're going to give to the user. Okay, so the lock we're giving to the user is this blue thing. The red thing is the guard, and what we do is we sort of wait, and if somebody else is checking the status of the lock, we get stalled here, but very quickly we go ahead and we're granted the lock, and we check and we say, well, if the lock's busy, we somehow go to sleep. Otherwise, we make the lock busy and we exit acquire. So notice that you never exit acquire in this implementation and in the previous one for that matter until you actually have the lock, in which point you exit acquire. Okay? Now, you could say, well, why is this not busy waiting? The point here is that the busy wait, which is in that while, is very fast. And it's really only waiting, it's only contending with other folks that are actually trying to figure out what the status of the lock is, not waiting for the lock to be released, okay? So were there any questions on this implementation? Now notice something that it wasn't in our previous, by the way, what does test and set do? Does everybody remember? Anybody? Go for it. It reads the value and then writes back a 1 simultaneously. So it doesn't write back the value, it writes back a 1. So read, write a 1 atomically so nobody can get in, and as a result, if you see a 0 coming out of this, then you know that you got the lock. And if you see a 1, you know you don't. Okay? Now, I want you to notice something. Notice this comment here. Guard equals 0 on wake up. So first of all, we somehow put the thread to sleep and set guard to 0 so that other folks that are trying to check this can go forward. But furthermore, when we get woken up, we're going to assume that guard is 0. And that's why we can put guard equals 0 in this else arm. Here is a different version, which is subtly different. And if you notice, this one looks more like our disable and enable interrupt. See that? While is the grabbing the, disabling interrupt, and this is like enabling interrupts. See how that's on the, around the whole critical section? And so Notice, though, that this is only an okay thing to do if we atomically, when we wake up, guard is back equal to 1 again. Okay, so if you took something where guard was equal to 0 on wake up and you put the guard equal 0 at the bottom, you would actually introduce an extremely subtle bug. Okay, because the person that was waking up already has the lock now. They set guard equal to 0 on exit, and somebody was checking the lock and they had just grabbed the guard and you just pulled the guard out from under them and suddenly your lock is not working. So I wanted to point this out just because you got to be careful to think about all of the arms of your synchronization, which is why this particular lock implementation is extremely small so that you can stare at it and kind of get it correct. All right? Are there any questions on this difference? Yes? So the bug is, suppose that I don't tell you this comment here, okay? So whoever wrote my go to sleep and set guard equal to 0 didn't tell me what happens when I wake up again. And I did this guy. Okay, so I put guard equal to 0 here, but guard is actually equal to 0 on wake up. So the problem is that I wake up, guard is equal to 0, and before I get down to this arm to set guard equal to 0 again, somebody comes in and guard gets set to 1 because they're playing with stuff, and I go ahead and I set guard equal to 0 out from under them. And I've just sort of screwed up the invariance on the lock there. All right, I'm not going to spend a long time on this now. Feel free to come and talk at office hours or whatever. But I wanted to point this out. You've got to be very careful that you understand your synchronization. Okay. Now, let's go through this other one, because this one is pretty simple. And we have two threads, A and B. The thread A is running. Thread B is on the ready queue, so it's runnable, but it's not running. Everybody understand the distinction? Okay. And now, thread A comes along, and they're going to acquire the lock. So they're going to run the acquire routine, which starts off by disabling interrupts. Now notice, by the way, that this means this has got to be in the kernel, because the user can't do this. So acquire and release are kind of system calls in the way that we've defined this particular lock. Okay, so we've disabled interrupts. Now notice that value up here is 0, so nobody has the lock. Okay, so we come through, value is not equal to 1. We go through to this else arm. We're going to set value equal to 1. We're going to become the owner of the lock. Now, that owner link is not a real anything. It's just bookkeeping for me to you to let you know that the thread that's got the lock is A. However, how do I know that that's A? I know it's A because in a moment, thread A called acquire and is going to get to return from acquire and keep going. So we know A has the lock. Okay, but this is just bookkeeping. Okay, so we re-enable interrupts, we come back, and now we have the lock. Thread B is still in the ready queue, so he hasn't gotten his quantum yet. And we start running the critical section. Now, you could say, well, gee, there's no contention for this critical section because the only one running is A. Therefore, why go to all this trouble? Well, first of all, because I'm making you go through the trouble that's on my slides. But the second part is that, the scheduler is a fickle thing. Remember how the scheduler is going to reach out and grab you at the wrong time because that's what schedulers do? So we're running this critical section, and all of a sudden, the scheduler is invoked by, say, a timer interrupt or whatever. So, of course, part of that is you go into the kernel, you disable interrupts. And, of course, what's going to happen when we reschedule stuff? Well, first of all, thread A gets put on the ready queue because it's not actually running anymore. Thread B gets to run. And then we're going to exit back to user mode with thread B running. And now thread B gets to go. So now notice some interesting scenario here. First of all, A was halfway through the critical section, not done yet. Ain't done yet, right? And B is about to try to acquire the critical section. So if somehow B gets to run the critical section, we might have a problem. So we better hope it doesn't, right? So B comes along, it's going to run lock acquire, which disables interrupts. And now what? Well, is value equal to 1? Yes. Oops, somebody else has the lock. So notice we got to go to sleep here and re-enable interrupts somehow so that somebody can run. Well, that's going to be, when we go to sleep, you actually go into the scheduler, and the scheduler is going to do what? Well, first of all, going to sleep means that B is now on the wait queue. It's not running. And the scheduler, by the way, if you figured out that schedulers are dotted lines, is going to pick A again to run and re-enable interrupts. And now A is running again, and B was prevented. Okay, now isn't PowerPoint wonderful? So it lets you draw all over the screen, and you guys are pretending to understand what's going on here, right? No. So let's pause here for a section. Notice that the scheduler has actually been invoked twice, and somehow our critical section has been respected. Okay, that's a good thing, right? That's what we were trying to do with all of this. And now we're going to get down to the end of the critical section, and A is going to release it. So it's going to call the release routine, which is going to disable interrupts. And it's now going to say what happens here. Well, is there anybody waiting? What's the answer to that? Yes. So what we'd like to do is take the thread off the wait queue and get it ready to run. Ready? Here we go. Dun, 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 dun. Okay, and that is actually an implicit transfer of ownership of the lock to B because, well, A has given it up, right? It's running lock release. And at that point, we re-enable interrupts, and we come back, and notice that this scenario is an interesting one. So first of all, A is out of the critical section. B is ready to run. So the fact that it's on the run queue means the scheduler could kick in any time. All right? And A is still running. Okay? Because just because we released the lock doesn't mean that B runs immediately. All right? We say that again. Just because we release the lock doesn't mean somebody who is waiting for it runs immediately. All it really means is that guy gets runnable again. Okay, and now we run for a little while, and whoop, the scheduler kicked in again. And now what's going to happen? Well, the scheduler is going to look and see what other threads are runnable right now. Well, there's on the ready queue over there is thread B. So it's going to pick up thread B and get ready to run it. So first of all, it puts thread A back on the ready queue, marks B as runnable, and B picks up right here after sleep. We come out of sleep. And what do we want to do when we come out of sleep? Well, it better be the case that interrupts are disabled still. Well, that's what the scheduler does. We go back to the closing of the acquire, which re-enables interrupts. We exit acquire from thread B, and we start running. Okay, end of animation. So, what do you think? Questions? Yes? So you'd like to have 20 thread Bs. Okay, first of all, that's confusing. So how about C, D, E, F, G? Okay? If you have a whole bunch of them, either they're not trying to acquire the lock, they're busy doing something else, or they're trying to acquire the lock, and they'll notice that somebody's got it, and they'll get put on the wait queue. Well, so you're asking what happens if A depends on B, depends on C, depends on A. Okay, not a cycle. That's good, because in a couple of lectures we'll say that's just bad, right? That's a deadlock cycle. So, well, if there's really a dependency, I want you to think that through. If there's a dependency that A depends on B somehow, the only way that could be expressed in a locking scenario is right here. We've got B depends on A, and that was set up implicitly by the calls through the call graph here. Okay, so it'll work out. Or you've got a deadlock. Those are kind of two options here. Okay, but we haven't done sophisticated programming yet. We've just got a lock, which, yay, we got a lock. Give yourself a hand. You got a lock. Yay, everybody. Right? Okay. Any other questions? The reason I do an animation like this, despite the fact that it's, fun to do, is that I think it gives you a better flavor for how many moving parts there are in a locking scenario like this. Hopefully this helps rather than confuses. But if there are no more questions, I will go on. Okay, question, yeah.
This may be a silly one, but does the scheduler have any insight into whether a thread wants to or have a lock, or does it just notice the thread ready or blocked status?
That's a great question. Does the scheduler have any insight about whether the thread is blocked or not, or how it's blocked? Right now, we're assuming the scheduler has no information. So the only thing the scheduler's only degree of freedom right now is to look at the ready queue and choose something. Okay, and from the standpoint of correctness, the assumption ought to be that it chooses the exact wrong thing to screw your algorithm up if you weren't careful. Right? Once we get a little further into scheduling, we can, like next time, we can talk about how schedulers could have more information about who depends on whom. Okay, and maybe make a decision to avoid deadlock. That's kind of where the banker's algorithm comes into play. But for now, the scheduler has no idea. Good question. All right, any other questions? Good. All right, so the other thing that we talked about just before the end of the lecture was about semaphores. And if you remember, a semaphore is like a non-negative integer with two atomic operations, P and V. The P operation basically waits for the semaphore to become positive and then decrements it by 1. And the V operation basically increments the semaphore by 1. And the interesting aspects about P and V is that if the integer is 0 and you go to try to do a P operation on it, you'll actually go to sleep. And V, when it increments from 0 up to 1, if it notices that somebody is sleeping, it'll wake them up. Okay, and the key thing about the P and the V operations is they're atomic. And so the fact that it says an atomic operation that waits for semaphore to become positive, then decrements it by 1, everything in that sentence happens all at once, or it doesn't happen at all. That's what atomic means. It either happens or it doesn't happen at all because you scheduled something else. Same with the V. Okay? And the only time you can set the integer directly is when you initialize the semaphore. And, in fact, the proper interface to semaphores is you can't even see what the value is. You have no idea what that is. It's not a provided API. Okay. And we looked at the semaphore from the railway where we have value equal 2, and as the train goes to the semaphore, that's this stoplight, it executes a P operation, goes through, the value goes down by 1. The next one executes P, the value goes down by 1. And now when the third one comes along and tries to execute a P operation, it gets put to sleep. And now when one of the trains leaves, it executes V, which wakes up the train that was on the other side, and it gets to go through and immediately decrements the value by 1, and so on and so forth. Okay? So those were semaphores. Were there any quick questions about semaphores? Because you're now playing with semaphores, right, in your project, so good fun. Here was a full solution on how to use semaphores for a bounded buffer. And notice, and the bounded buffer was basically the Coke machine. And notice that we have 3 semaphores. One that's talking about sort of how many full cans of Coke there are. The other one about how many empty slots there are. And you might say, well, this is, they're related to each other by buffer size. But in fact, semaphores are not just the integer. Remember, they're also a wait queue. So what we've got by having these two interrelated things at the top is they're 2 different wait queues, one for students, one for Coke machine delivery guys. And the third one is a mutex, which is used as a lock. And if you notice, what we said here is when we produce a new can, we first wait until there's space in the machine, then we grab the mutex so that we don't screw up the queue. We enqueue something, we release the mutex, and then we wake up anybody waiting for the Coke. And then the consumer basically says, if there's a Coke, then go ahead and grab the mutex, which will let us dequeue safely, release the mutex, and then tell the producer we can use more Coke in the machine and return the item. And notice, by the way, that there's an implicitly interesting thing here. I should have said consumer returns an item, because the way we've set this up, we never dequeue unless there's an item in the queue. because otherwise we go to sleep up here, right? And if there's an item in the queue, that means we return something that's a non-null can of Coke. If we return a null can of Coke, that's just an annoyed, sleepy student, right? Okay? So in our future examples like this, we're going to have some semantics on what we think we can be returned from the consumer. So were there any questions here? Yes? So a semaphore here, notice that we're using the semaphore to represent the full extent of how many cans of Coke could be in the system. So this is more than 0 or 1, whereas this mutex is a good example of a lock. In fact, it is a lock. So the answer to your question is basically that whenever we're dealing with a scenario where there's a resource constraint that's more than just yes or no, then we'd use a semaphore with something bigger than just a 1. In fact, as I mentioned last time, you could initializing a semaphore with a value of 0 is a really interesting thing as well, which says I could immediately go to sleep waiting and use that to signal somebody to wake up by doing a V on that operation. That'll wake them up. Okay, good. So and then we talked about, so basically the full slots wakes up anybody sleeping on full slots .p, and empty slots V wakes up anybody on empty slots .p. Okay. Now, yes? Yes, you can absolutely use a semaphore set to 0 as a way to signal somebody, yes. In fact, you could use them. I think I showed last time the idea of a thread join made with a semaphore, right? Okay, so why is there the asymmetry? Well, that's because the producer checks for an empty buffer and then when he puts a can of Coke in, wakes somebody up, whereas the consumer checks for a full buffer and after drinking a can of Coke or getting a can of Coke, wakes up the producer. So we're using them in asymmetrical ways. Is the order of the P's important? Yes. We showed that could cause deadlock last time. Is the order of the V's important? No, because it might cause scheduling efficiency issues, but nothing more. No deadlock. And what if we have 2 producers or 2 consumers? Yes, it works. Okay. Now, let's talk about monitors, which we were rushing into at the very end. So the semaphores that we were showing you is actually a pretty big step over locks, because just having a lock means that when we want to put somebody to sleep, we don't have any really good way to do that other than having a yes-no scenario. Whereas what we saw previously here was we have this empty buffer and full buffer, which are queues on which we can put folks to sleep that have different constraints on them. So that's a big step over a lock. Okay? If you think about how to get a semaphore out of a lock, you have to do a little work. Okay? Now, the problem is that semaphores, as I've defined them here, are actually dual purpose. They could either be used as a mutex or as a resource constraint, and that can get very confusing. So the fact that we could flip the P's around might not have been obvious until somebody explains it to you. And think about code that you haven't looked at for 2 years, and you suddenly stare at the code and there's different uses of semaphores. You can imagine that could get messy, right? Unless you have a lot of comments. So a cleaner idea is to go back to using a lock, but introduce a new thing which we call a condition variable. So the lock is going to be for mutual exclusion, because we're always going to need that, and the condition variable is going to be back for a scheduling constraint. And the definition of a monitor is really a lock and 0 or more condition variables, where 0, by the way, is not really terribly interesting, but we'll show you that in a moment, for managing concurrent access to data. And there's a bunch of languages, Java is a good example, that provide this natively, and others provide locks and condition variables as library and kernel implementations of them, okay? And here's a graphical view where what you see here is really, some would say this is the monitor. It's a bunch of shared data with a queue, of a lock queue that's about entry. Okay, so you when you're about to try to deal with the monitor, you first have to grab a lock. And then a bunch of sleep queues, which are the condition variables, which represent threads sleeping because the conditions are not quite right for what they need to do. Now, if you think back to the Coke machine example, we had at least two different examples of sleeping, right? We had sleeping because there wasn't enough Coke, and then we had sleeping because you'd have to try to put Coke into a full machine. And so we have at least 2 Qs worth of queuing and the mutex. So, on the face of it, this doesn't look like a big step forward. But let's take a look a little bit more about what this is. And first of all, I'm going to put this idea out for you. So a condition variable, the key idea is you can go to sleep inside of a critical section on a condition variable. Okay, now I want to pause on that because that's a little weird, but it's only weird if you think it through. So remember what happened when we swapped the P operations and we got deadlock? So that was really because we swapped and we grabbed the lock on the critical section, the mutex, and then we went to sleep, and that deadlocked the system. But with the condition variables, we're going to be able to do that, and that's because they're condition variables. I will say that up front. By the way, is that echo driving anybody else nuts? Let's see here. I wonder if I can turn this down a tiny bit. Hold on. Let's see. Testing. Oh, that's better. Okay. Is that a little better? All right. We'll see. Okay, so, no, it's not better. But anyway. So let's look at a very simple example. I almost hesitate to do this, but I want to say that just because we call something a monitor doesn't mean that all of your previous knowledge of things you understand go out the window. So a monitor is a lock with 0 more condition variables. So let's put in 0 condition variables, and voila, here's a queue that works with a lock, right? So the way you add something to the queue is you grab the lock, you unqueue the item, you release it, and the way you remove it from the queue is you grab the lock, you dequeue it, you release it, the lock, and then you return the item you got back. Okay? This is locking 101. But can somebody explain to me why I put a lock where I did? Why do I have a lock, acquire, and release here? Somebody give me a simple reason. Yes. Yeah. So we only want one thing modifying the queue at once. So if we have multiple queuers and dequeuers and they all get in there and they start messing with the pointers, they're going to screw the queue up. Okay, so we need to lock, acquire, and lock, release just to prevent the queue from getting messed up. Look at what's interesting here, though. Down at the bottom, I point out that the way this language works here, the way we've written this, when we acquire and dequeue an item, there may not actually be anything on the queue, and so we could return a null item here. And that's probably undesirable, because why return from removed from queue without an item? Now, maybe you put it in a loop and you try it over and over again, but that sounds a lot like busy waiting. Wouldn't it be nice if we could somehow just go to sleep when there's nothing on the queue and then wake up with an item on the queue when there is something on the queue? Okay, and this is very close to the Coke machine example, but we're going to do this in the form of a monitor. So let's before we do that, let's talk a tiny bit more about condition variables. So how do we turn remove from queue into something that basically waits until there's something on the queue? And we could do this some ad hoc way by keeping a count of the number of things on the queue, but it's a little error prone. And so let's see if we could do this a little differently. We're going to have our condition variables. And once again, a condition variable is a queue of threads waiting for something inside a critical section. And we're going to allow sleeping in the critical section by atomically releasing the lock when we go to sleep. So all of those of you out there that are worried that I'm somehow violating, basic physics or something by going to sleep with the lock and there's no deadlock, what we're going to do is this is a programming paradigm. It's a way of thinking of what's going on, and the system is going to fix it so there's nothing screwed up by going to sleep with a lock. Okay, so but we're going to think of this as if we actually went to sleep inside the critical section. Okay, you guys willing to go with me on this journey? Okay, so this is a way of designing code. Okay, and remember the contrast with semaphores is that a semaphore, if you go to sleep with a lock, you're hosed, right? Game over. Okay, so now we have 3 operations. One is a wait operation where we have to give the lock. If you're doing this with basic C, you actually have to give a pointer to the lock. And what wait will do is it'll atomically release the lock and go to sleep. And then before you return from wait, it'll reacquire the lock. So we'll get that illusion that we've held the lock the whole time. Signal says wake up one waiter, and broadcast will wake up all the waiters. So the rule is, in fact, just the opposite of what you might have thought otherwise, which is you always hold the lock when doing any conditional operations. And there are some folks, like there's a barrel paper when these first came out that says you might be able to do signal outside the lock, but we're going to not do that for now. So before you do any of these, you have to hold the lock. So here is a new version of our buffer with a conditional variable called data ready. And what happens? Well, when we add something to the queue, we grab the lock, we enqueue it, we signal somebody who might be sleeping, one person, we release the lock. Okay? When we remove from the queue, what do? We acquire the lock, because we always do this, right? Always acquire the lock. And then we go in a loop and we say, well, as long as the queue's empty, wait on the lock. And then we wake up and we'll check whether the queue's still empty and so on. But then eventually we'll exit this while loop, and now we know for a fact that the queue's not empty, and we'll dequeue an item and we'll release the lock and continue. Now, don't worry about the while. We'll fix that in a moment. You guys can understand while in a second. But what's more interesting here is this question that you might have in your mind, which is, how do I know when I wake up and I've checked that the queue really is not empty, and I go to dequeue something, how do I know that somebody doesn't dive in there and steal it out from under me? Yeah. I have the lock. Okay, now look at that. So this is why thinking in monitor think is important. So notice I've grabbed the lock, I've checked my conditions. As long as the conditions are good, I just dequeue and I release the lock. There is no releasing of the lock in that while loop in monitor think. Okay, you're all thinking in monitor think. All right? Everybody with me? So once I've checked the condition, I dequeue it, I release the lock, I return the item, and I know that that item is there because the queue's not empty. Okay? Yes? So you're worried about if I don't release the lock in here, how do I add items up there? Well, remember now, this is monitor think. In monitor think, we just check the condition and we dequeue if the condition's good or not. Otherwise, we wait. And under the covers, they'll release the lock so that somebody can come in and add it and so on. But that's under the covers. Okay, so you can't totally forget everything you know is actually going on. But you'll see when we get to the reader-writer example, which is kind of at the last part of the lecture, you'll see why it's useful to think this way. Okay? Now, so the signal, in principle, wakes up somebody. So if you go to sleep because there's nothing on the queue and somebody adds to the queue, you'll be woken up. And one item will get woken up. So if there's 12 people sleeping on the queue, you'll end up with one of them gets to dequeue the item. All right. Now, questions before I go on? Any other questions? Yes? So, again, this is in monitor think. So the way to think about this is the reason I'm acquiring the lock is so that I can safely check the condition. Safely checking the condition means I'm going to find out right here and now either there is something on the queue or there isn't something on the queue. And I'm going to do that inside the lock. And assuming that the condition is met, that there's something on the queue, then I'm going to dequeue it and I'm going to release the lock. Okay? And the reason I want a lock there is so that I don't make a decision that there's nothing on the queue or there's something on the queue and somebody comes in and screws it all up for me. So putting the lock, acquire, and release where I've got them there is that I can check a condition, and assuming the condition meets my needs, I can go ahead and immediately do something based on that condition without anybody screwing it up. Well, because, in fact, when I discover the condition's bad, I go to sleep by dot waiting. Okay, now, and when I go to sleep by dot waiting, under the covers, it lets other people come in to fix it for me. Okay? But the way to think, I understand it's weird, right? This is a weird way to think the first time you see monitors, but once you get thinking this way, it's much cleaner, and you can do really complicated stuff easily, and I'll do something complicated relatively easily, or relatively complicated fairly easily. You pick the balance toward the end of the lecture here, okay? All right, so now, tomorrow is the first design document, so make sure that you guys are aware of that. Yeah, we're moving along. And then subsequently to that, we'll be scheduling design reviews. So be watching for all of that on Piazza. Midterm is also coming up a week from Thursday. And I actually have the room assignments, but I haven't put them up on the sheet. I'll do that, but it's from 8 to 10. Okay? And then, yes, question? This week. Yeah, they'll be, if you have any conflict questions, we'll take care of them this week. Sure. You can, as a matter of course, you can always send a follow-up email if you haven't heard from a faculty member for a while. That's usually not a bad idea. If you send too many of them, though, then they get annoyed. Anyway, no, definitely send up follow-up if you haven't heard. So the other thing is closed book, no calculators, one double-sided letter-size page of handwritten notes, so you can write anything you can fit, you can write. But no microfiche. Okay, you can't take your book and shrink it down and print it out on a single piece of paper and bring a magnifying glass. We don't allow that. Okay? And we're going to cover lectures 1 through half of 11, which is kind of up through deadlock. Okay? No address translation or anything. So, questions? All right. Now, let's talk about this while loop. So, we need to be very careful to put things in a while loop, and the question is why? And the real answer is because you might have thought this was right. You know, if the queue is empty, go to sleep. Doesn't that seem reasonable? Simpler, right? Why didn't we do this? Well, we didn't do this because it depends on the type of monitors you've got. There's 2 completely different types. There's a Hoare-style monitor, which is named after a British logician, and there's a Mesa-style, which is named after a Xerox PARC operating system. And the first one is, logically cleaner, but really a mess to implement. And the second one is a little bit more difficult to deal with, but much cleaner to implement. And most systems are all Mesa style. Okay, but I'm going to show you, for instance, what does the first version look like. So in the first version, suppose that we're going to signal somebody who's sleeping over there. So what happens is we do the signal, and the monitor hands both the lock and the CPU off to the sleeper immediately. One sleeper, and they get to run, they do their thing, and then on release, they hand the lock back to the original person who continues. Now, if you do this, what's nice about this is you can say, well, I know for a fact that I check this condition, I go to sleep, and I know that the only way I'm ever going to wake up is if the condition's absolutely true, in which case I get to go forward. Okay, but this lock handoff thing gets messy. And the other thing that's a little nuts about this is if you think about the scheduler, you don't want to schedule too frequently because there's overhead involved and you're screwing up the cache and all that sort of stuff. The problem with this is this requires an immediate handoff to a different thread and then a hand back. Okay. The Mesa monitor is a little different, because what happens is the only thing that happens with a signal operation is you put the waiting thread on the queue, and sometime later the scheduler schedules them, and that's why we have to check, because it's possible that somebody got in there and stole it out from under us before we actually got to run. Okay? Now, I have a wonderful animation to show you how this works. Okay? So here we go. Why while? So, here's our add to queue and our remove from queue. And let's take a look. So if we replace while with if, then let's see what happens here. Ready? So we have T1 is on the is running, and it's going to acquire the lock, and then it's going to say, is the queue empty? And yes, it is. And so we get put on the wait queue, and at that point the lock is transparently underneath the covers released, and meanwhile T2 can run. So notice that T1 tried to grab something off the queue, and the queue, as you see up here, it has nothing in it, so this guy is sleeping. Okay? And we come along. So we're going to add something to the queue. We're going to enqueue an item. See, there's an item. Everybody see the item? Yep. And then we're going to signal, which wakes up T1. And meanwhile, what does wake up mean? Wake up means you're on the ready queue, but not running. And meanwhile, T3 happens to come in that section, and it tries to run. So it's running. It gets to run before T1, so it acquires the lock. It says, is the queue empty? No, we're going to dequeue it. So notice that there's no item on the queue now. And T3 is very happy. T1 comes back, exits, says, oh, okie doke. I got signaled. Time to dequeue, and oops, there's nothing on the queue. Okay, so notice that what happened here is really, because we didn't have a Hoare-style scheduling, but rather a Mesa-style, this signaling did put T1 on the ready queue, but didn't run it immediately. So the fact that another thread got to come in there and grab the queue item means that now whatever invariant we thought we had enforced by that if is now violated, and we get an error. Okay? Good, everybody? Now, if we look at what happens if we have the while in there instead, then we would wake up in this same scenario from the previous slide. We'd go back to the while. We'd check it again. And no, back to sleep. Okay, so just because you get woken up in a Mesa-style scheduling doesn't mean you get to immediately run, and therefore you got to recheck your condition. But what you do know for a fact is between lock acquire and lock release, when you're in here checking this while, if you decide the queue is not empty and you immediately dequeue, you absolutely will get your item, because think this as I've got a lock around the check. I checked it, I got to go. It's only when you go to sleep that other folks can get involved. Okay, ponder for a sec. Question, yeah. Well, so the question here is, how would this work with broadcast instead of signal? So the great thing about this while checking condition is if you get woken up for reasons that are not quite meeting your constraint, it's okay because you always check your constraint and go on. Whereas with the Hoare style, you actually have to be exactly careful, and you can only signal somebody. You have to check the condition exactly, and you can only signal somebody if they can absolutely run again. So that is another advantage of this Mesa-style scheduling, is you can be sloppy about your condition in signaling, and we'll show you that later in the lecture. Good question. Good question. Anybody else? So, all right. So we're going to define the readers-writers problem, and we're going to make a little headway on this, and then we'll take a break. But the motivation here is a shared database. We got two classes of users: readers, who never modify anything, and writers, who read and modify the database. Now, could we use a single lock on the database? I actually saw a Piazza question sort of similar to this. Could we use a single lock on this database to make this correct? How many people think a single lock could make this correct, where we always lock the database, we do our operation, we unlock it? How many people think single lock works? How many people think a single lock doesn't work? How many people are not sure? Okay, all right, not sure. So I will tell you a single lock is fine, but a single lock is probably not great. Okay? So a single lock will always get you correctness in a scenario like this, because you lock everything up and one person at a time goes through that narrow door. But given what I've described here with readers and writers, what do we lose out here? Yes?
The readers can technically all at the same time because they're not modifying state of the database, but the writer is one that has to modify state of the database or lock depending on modern state.
Great. So what she said was that you could have many readers going simultaneously and there's no issue. But when a writer comes along, then you got to make sure there are no readers in the database right now, and while the writer's doing their work, there can't be any other readers or writers. So the thing we need to, if we think about narrowing the security, we narrow security on this system when a writer's happening and we only allow one writer at a time. And readers, we can have many readers at a time, but never readers and writers should never meet at the same time, because potentially the writers are screwing up all sorts of invariants about the database. Okay? Everybody with me on that? Great. So, many readers at the same time, one writer. All right. So, we're going to have correctness constraints on this. Readers can access the database when no writers. Writers can access the database when no readers or writers. And only one thread manipulates state variables at a time. Okay, so what is a state variable? Well, let's look. So the basic structure is the reader, wait until no writers, access database, wake up awaiting writer, if there is one. Writer says wait until no active readers or writers, access the database, and then wake up waiting readers or writers and keep the constraints up there. So it seems like we could specify this problem with a bunch of variables, like, how about, 4 integers and 2 condition variables. How's that sound? Now, you're looking at this like, what? But in fact, these are kind of the obvious thing, right? It's the number of active readers, the number of waiting readers, the number of active writers, and the number of waiting writers. And what I want to show you is you can come up with a pretty simple set of invariants on AR, WR, AW, and WW that will meet our basic correctness at the top. And we put readers and writers to sleep on condition variables when they are not allowed to go forward. And the trick is we're going to specify our potentially medium-sized, complicated constraints with a monitor, which is going to make it a lot easier to do this. We could not, what we're about to do, we could not do well with only semaphores. You'd go nuts, okay? Now, why don't we take a brief break, and we'll come back, and we'll see how to do this. All right. Now, you guys have been doing a good job of suspending your disbelief on all of this, so let's see whether monitors really buy us something. So what does a reader look like? So all monitors style of programming or monitor pattern always starts by acquiring a lock, checking some conditions, and releasing the lock. And then doing the main thing, and I'm going to talk about these conditions in a second, and then sort of grabbing the lock, checking yourselves out, and ending. So notice that pattern of grabbing the lock, checking invariance, releasing the lock, doing something, grabbing the lock, updating invariance, and releasing the lock. And so let's look through this. So what are the invariants? Notice on the reader side, what we're going to say is as long as there's an active writer or a waiting writer, and I'm going to assume that our invariants are not going to cause AW or WW to go below 0. Okay, we won't screw that up. Then we're going to become a waiting reader, so we're going to increment the number of waiting readers. We're going to go to sleep on, or wait on the condition variable for readers. And then when we wake up, we're going to decrement because we're no longer waiting as a reader. And we're going to go back and check our condition again. Okay, and notice that the way to think about this is I've grabbed a lock. Everything inside of this lock, by the way, we're going to release the lock down here. Everything inside that lock, I can do arbitrarily complicated stuff on integers and what have you because I've got the lock. Okay, now you got to ignore the fact that we go to sleep with the wait there for a moment. But everything inside those locks, I'm going to catch the waiting. I'm going to, check the number of active writers and waiting writers. Why do I know that summing these two together I can do and make some decision based on it? Well, I've got the lock, and therefore there's no way a writer could come in and do anything to those variables. They're taken, right? They're locked out because I've got a lock. Furthermore, I can increment this WR++. This is absolutely not an atomic operation to increment. Why is that? That's WR equals WR plus 1, right? If you thought plus plus was somehow atomic, it's not, okay? On a lot of processors. Some of them actually have an increment. But anyway, that goes without saying, or maybe I shouldn't have said it. So anyway, I can do the WR++, I can do the WR minus minus, I can do the AR++ because I'm inside the lock. Okay, I'm not going to overstate this. You guys got the idea there? I'm doing stuff inside here that I don't have to worry about anybody coming from the outside and messing those constraints up. And this while loop says I've checked my conditions, and then if they're not right, I go to sleep on a condition variable. You all see where the terminology comes from there, right? So, good. Now, what are those conditions? Well, once again, if there are any writers in the system at all, either somebody who's actually writing the database or somebody who's waiting to write the database, I go to sleep, and I keep my statistics up like, gee, I'm a waiting writer now, so I'm incrementing. And then when I'm not waiting anymore, I'm no longer a waiting writer, I decrement, okay? And then when I make it through this, I increment the fact that I'm now an active reader, and then I exit with the lock, at which point I access the database. Okay? And on exit, what happens? Well, I grab the lock because I'm going to update the invariance. I decrement the active writer count because I'm no longer an active reader count because I'm no longer an active reader. And then I say, look, if there are no active readers and there's a waiting writer of some sort, go ahead and wake them up. Wake up with signal one writer. Otherwise, just release the lock and go on. Okay, so digest and ponder. So this is a pattern. The pattern is I use the lock to protect a bunch of variables, maybe one, maybe more, that are checking invariance and keeping invariance. And if something's not right yet, I go to sleep. And I'll wake up and I'll recheck again. So what's good is this signal down here doesn't actually have to be perfect. In fact, I could just signal after I'm done, and the thread might wake up and decide that things aren't right and go back to sleep again. But instead, I'm going to try to be smart down here and only execute a signal if I really do want a writer to go forward. Okay? and then I release the lock. Now, why am I releasing the lock here? Somebody walk me through why this. Yes?
Because you can have multiple writers, or sorry, multiple readers at a time.
Uh-huh.
And you want to release the lock so that other readers can get reading.
Right, correct. So the simple thing is I'm releasing the lock so that other readers can check themselves into the system. But in fact, the first thing you said is even more correct, which is there could be multiple readers and writers out there in the world that are trying to access the database, and by releasing the lock, I'm giving each one in turn the ability to check the invariance and either go to sleep on the right condition variable or go forward depending on the conditions. And so I have to release the lock in order to let the other folks come in and check the invariance. So this pattern is kind of like a meta locking pattern in that I'm using the lock to enforce some more complicated invariance. And it's actually, this code may look complicated, you guys, but this is a remarkably simple way to have a fairly complicated scheduling pattern that I've put on my database. Okay, now let's look at the writer side. So the writer side says, well, we require the lock, same pattern, right? Now we say, well, if there's an active writer or an active reader, I got to go to sleep. Okay? And what do I do? Well, I increment the number of waiting writers. I go to sleep on the condition variable. And then when I wake up from that, I decrement the number of waiting writers. I check my condition again. Same pattern. And, everything's great. There's no active writers or active readers. I now become an active writer, and I release the lock, and I access the database. Okay, now, hopefully there's something that you're worried about here, which is like maybe waiting readers. We'll get to that in a second. And what do we do on exit? Well, I'm done writing, so now I grab the lock. I'm no longer an active writer. And I say the following. If there's a waiting writer, go ahead and signal them, one of them. Otherwise, if there's a waiting reader, go ahead and broadcast to all of them. Go ahead, wake up. Anybody who's an active reader, time to go. And then I release the lock. Now, what seems to be not covered here? Anybody have any lingering doubts? Yes? Well, okay, great question. Shouldn't I have a lock in place so I can write safely? Well, in fact, the lock is really the invariant checks up at the top. If you think through what we've got with both the readers and the writers entry, we don't let anybody into the database unless the conditions are correct. And in the case of a writer, notice we don't let anybody into the database if there's either an active writer or an active reader. So therefore, by the time we release the lock there and get into the database, we know for a fact there are no readers or writers that are actively using the database right now, and we can go forward. So that there is no lock around this that's needed. The lock is around the invariant portion at the top and the bottom. Yes, question?
I mean, when we're running like the critical section where we're writing, we're assuming that even if you switch to another thread, nothing's going to access it.
Well, okay, so I can see we have some doubters in the audience. So the question here was I'm giving you a hard time, right? So the question is, do we know that once we've made through this and we switch threads, how do we know that things aren't going to get screwed up? Okay, right? That's the question. And the answer is, all threads that access the database have to go through either the writer heading or the reader heading. And threads that don't adhere to our constraints, which are basically either multiple readers or one writer, and never the reader and writer shall mix, they will get put to sleep in their corresponding condition variables. And so the fact that there is a writer here working on the database means that it's not possible for anybody else to get through the headers to violate our constraints, which are multiple readers, one writer, and never the twain shall mix. Okay? It's funny. It's like you go. When I first saw this code many moons ago, you go through this stage where it's sort of like stages of grief or something. It's like, that can't possibly work. And then it's like, yeah, it kind of looks like it might work, but I don't believe it, and I don't like it anyway. And then you get to a stage eventually where it's like, that's really cool. Right? You guys are not quite there yet, but you will be. But notice that with the monitor, we can construct interesting invariants like this one to access a database using, for instance, our 4 integer variables and our, and our 2 condition variables. And think about this is an exercise for the reader. Try to figure out how to do this with only semaphores. Okay? It's doable, but it's really painful. Okay? It's a challenge accepted, right, to the readers, yeah. Let me ask this. How many people looked at this condition and said, well, wait a minute, but what about the waiting readers? Did anybody wonder about waiting readers? Can somebody tell me why I don't check with my waiting readers? Yes. So, yes. So the interesting thing here is there is an implicit priority. We've given writers priority over readers. So if we have a writer that's going to come along, we will in either a waiting one or a brand new one, we always give them priority over readers with this particular code. That's not, you could say, well, that's either a good thing or not. But over this particular code, we've given priority to writers over readers. And you can see that in several places, like down here. If the waiting writers are greater than 0, signal a writer, otherwise signal waiting readers, right? And if you look at the previous reader code, it's kind of like, well, obviously we have to let any active readers go forward because, they're all busy doing their thing on the database already. But once all the active readers have gone to 0, and we immediately check waiting writers. We don't bother checking waiting readers, okay? Because if there are any waiting writers, we'll signal. Otherwise, you could argue, think this through as to whether there could actually be waiting readers to worry about here. Okay. Good. So, just to reiterate that. So if I have my number of active writers was clearly bigger than 0 because I'm a writer, if my number of active readers is bigger than 0 because I'm a reader, obviously it's at least 1, right? And I come down and I decrement from the number of active readers from 1 to 0. What is the value of waiting readers? Have to be. Has to be 0, right? Because if it were non-zero, we'd have a bug in our code because we would never put a reader to sleep under those circumstances. Okay. Good. Now, so let's through the power of PowerPoint. This is the simulation day. Okay, we're gonna walk our way through a sequence of operations. Reader 1, reader 2, writer 1, reader 3. And let's see how this works, okay? So, reader 1 comes along, tries to do the reader operation, grabs the lock. Is it safe to read? Well, we know that active writers plus waiting writers is 0, so we immediately come down here. We increment the fact that we're an active reader. We release the lock. Why release it here? Well, so the other people can go forward, right? We said that earlier. And then we access the database. All right. Now, meanwhile, R2 comes along. So, by the way, reader 1 is busy reading the database. So, reader 2 comes along, grabs the lock, and notice, by the way, that now we have 1 active reader up here. Okay? Now, are there any active writers or waiting writers? No. So, we increment the number of waiting readers to 2, release the lock, and now we got 2 readers busy reading the database. Okay? Meanwhile, so the reader's going to take a while. So now notice what's interesting here, by the way. This is kind of like how we avoided the busy waiting with the test and set lock. Remember how we used the busy waiting code to build a lock where the acquirer of the lock could take you could hold on to the lock for a long time in whatever you're doing, right? But you never busy wait very long. Similar idea here. We could imagine that readers 1 and 2 are busy working for a long time on the database. Days. Okay? And we've released all the locks in our monitor, so that means that nobody is prevented from at least coming in. Oops, sorry. So, here we go. Writer 1 comes along. We check. We say, are there any active writers or active readers? Yes, active readers, right? Look up here. AR is 2. So, we go to sleep. Notice that just before we went to sleep, waiting writers equal to 1. Okay? And W1 can't start because of the readers, and that's it. So now that waiting writer is sleeping. But the lock is kept, right? Well, from the standpoint of somebody thinking about invariance, we think about the lock being kept, but the fact that they went to sleep means the lock is released under the covers. Okay? Monitor think, right? Once you get the sort of the pattern down, it's a little easier to think. So, yes, the lock is released under the covers, which means that when R3 comes along, they can acquire the lock. Now, is active writers plus waiting writers greater than 0? Yes. So now this reader has to go to sleep. Okay? And it will release the lock under the covers. Okay, so what's our status? Now, R1 and R2 are going to spend several days accessing the database. I guess I said that earlier. This lecture is going to go on forever. W1 and R3 are waiting on the OK to write and OK to read condition variables. Okay? So nothing at this point is going to happen with W1 or R3 until something happens with the 2 readers. Because our invariants are preventing that from happening. Okay? Questions so far? Now, everybody with me? Okay, so R2 finishes. Okay, so when it finishes, it's going to do the exit code. It's going to check for lock acquire, decrement the number of active readers because I'm no longer active. Is active reader equal to 0 and waiting writer greater than 0? People are going like this, and then they're doing this, and then they're doing this. So that condition's false, right, because there's an active reader. Okay? So we release the lock, and nothing happens. Now, meanwhile, R1 finally finishes. And notice, by the way, there's nothing in this code that said that because R1 came in first, it had to be the first one out, right? We didn't make any constraints like that. So R1 finishes, the number of active writers goes down to 0, and now, is number of active writers equal to 0? Yeah. Is the number of waiting writers greater than 0? Yeah. Signal. Dun, dun, dun. All readers are done, and we're going to signal writer W1 to go forward. So, signal. Okay? At that point, this guy is going to wake up, come out, decrement the number of waiting writers, go back and check the while, which is now going to be fine. I should have put more simulation in there, but this gets a little old after a while. I'm going to increment the number of active writers, release the lock, and now W1 is busy accessing the database, and R3 is sleeping on the condition variable. Right? Yes, question?
If the OK to write wait releases the lock, the lock probably is not good.
That's a great question. Does everybody catch that? The question was, gee, if OK to write dot wait released the lock, what am I doing releasing the lock here? Well, I didn't have a blue bar there, but anybody know the answer to that question? Yeah.
When you're returning from wait, you give the lock back.
Yeah. So monitor think, you never released the lock. You got the lock, right? You acquired it, you released it. What's happening under the covers is, yeah, the lock's released, but you never come back into the code until you grab the lock again. So that's why the monitor think is okay. Yes, I grabbed the lock and I only release it down there. Great question, though. Okay? And I would suggest, if you go back and look at the code at the slides at the very beginning of the lecture, where I showed you walk through this kind of disable and enable interrupt lock, you'll see that this is very similar to that notion of disabling interrupts at the same time you go to sleep, and then you come out of that and you still have the interrupts disabled. Yeah. Good question. Great question. Okay? And so now I'm done. I'm going to decrement the number of active writers. Number of waiting writers is 0, so that's not going to happen. So I'm going to broadcast to all the readers. There's only one. Okay? And that broadcast will wake up our reader, who will decrement, access the database, and be done. And then we acquire the lock, and we release the lock, and we're done. Woohoo! All right, so there's your example. And notice how the way the monitor was used to protect the invariance at the entry and the exit. It's not used to protect the database, except through the invariance. Okay, but this basically this allows you to do very interesting things relatively simply once you get past the monitor think. Okay, now, can the readers starve? I mean, look, we got this entry code, right? While active writers or waiting writers are greater than 0, go to sleep. So what's the answer to this? Can readers starve? How many people think the readers could starve if a stream of writers keeps coming along? Yeah, absolutely. So all that has to happen is before the previous writer exits, another one comes along. As long as the writers just keep showing up, they will never get any readers, will never go forward. Okay, and that was by design. Could you do something more interesting? Yes. In fact, you could build a queue. You could have condition variables in an array, and you could keep track of intervals of arriving readers and writers if you wanted to, and you could make it totally fair. Okay? Question is the following. How many people think that, what's an argument for this architecture of my invariance being an okay thing? Can anybody make up one? Yeah, go ahead. So the actual code which handles the lock is fast. So I would actually say that's not a good answer to this question for the following reason. It's a good thought. But in fact, remember, writers could take days and a stream of writers could keep through. So this isn't necessarily about time for code. Yeah. Okay, you're guaranteed to have a collect read after all the writes that are pending. Yeah, I like that answer. That still doesn't help my live lock issue, though. Anybody want to make an argument why readers might not starve? That was a good answer, by the way. I like it. Yes. Yeah, there you go. Writes, you'd have to have some data that says somehow writes are much more infrequent than reads, and therefore this particular structure of the code is okay. Okay, maybe that's not true in your database, and then you got to do your invariance differently. But this one is kind of, it's certainly a thought that people often have that, because of the data of many types of databases and file systems, that there are a lot of cases where writers are much more rare than readers, and this could be okay. What if we erase the condition check in the reader exit? So notice, what if we just erase? What happens? Yes? Writers wait forever. Actually, the opposite happens. So it's going to... If any time a reader finishes, it's going to signal a writer to wake up. Does that violate the database constraints? Yes, go for it. Okay, but my question is, if you erased this code and just had OK to write.signal, would the database be violated? Yeah, go ahead. Okay, great. No, this is perfectly fine because when you wake a writer up, it checks its condition and goes back to sleep if the conditions are wrong. So what do we get out of Mesa scheduling is not just it's easier for the operating system, but you can be sloppy about the wake-up signals because you always recheck your condition. Good. Now, what if we turn signal into broadcast? Same answer. We broadcast, you've got 20 writers, you wake them all up, one, either they all go back to sleep or one of them wakes up, but the right things are going to happen because we keep rechecking our entry conditions. Okay, so that's why a while is particularly good. And the last one is, what if we use only one condition variable? So we put readers and writers to sleep on that condition variable. Well, we got to use broadcast instead of signal because maybe we need to wake up all the readers and writers are mixed. But fundamentally, it's going to kind of do the right thing because the while loops will all check the entry invariance. So we're never going to violate invariance, but the downside of this is we've woken up a bunch of threads which are then going to run code and then go back to sleep. So the downside of this is being too sloppy wastes some cycles, but you never violate the invariance. Okay, and I actually had here's the example of what we mean. We have OK to continue, and we could come up with some simple scenarios, and what you'd find is that we actually need to put broadcasts in places to make sure that, for instance, if we have a bunch of readers that need to wake up, we wake them all up and so on. Or if we have 5 readers and a writer, if we just do signal, we don't know that we get the writer that has to go forward woken up. So the downside of being sloppy is sometimes you have to be really sloppy and really put broadcast in a lot of places. Okay? All right. So now, are monitors and semaphores equivalent? Sure. Well, the locking is easy. We can just use a mutex, right? Can we implement condition variables this way? The answer is no. Can somebody give me a downside here? Yeah. No.
Because semaphores only have that value that you're initializing, so you kind of need more than that value. That's really more on what's needed, right?
No, not quite. There's a semantic problem here. Yeah.
You don't release the lock.
That's right. If you go to sleep with the lock, your system's hosed. Okay, so this doesn't work. Does this work better? Lock.release, semaphore P, lock.acquire, and then signal is semaphore B. Is this a better one? Now notice that we make sure to release the lock and then go to sleep. And signal does a V to wake us up. Does this work? How many people think this works? A couple of you. How many people think it doesn't work? Ooh. You want to give it a stab? Anyone want to tell me why? Okay. So the problem is that condition variables, as we've specified them, have no history. So if you signal and there's nobody on the wait queue, nothing happens. Whereas the problem with this is if you signal early and then do a wait, you'll just immediately go right through. So you don't go to sleep. Whereas wait always puts you to sleep. So this is fundamentally a difference in API. Okay? So basically you can see that these two things are a little different. So the problem with the previous thing is that P's and V's are commutative, and the result's same no matter what order they can occur. Condition variables aren't commutative. And if you think about it, the reason that you don't want condition variables to be commutative is you're checking a condition and you want to always go to sleep when the condition's violated. Whereas P and V, if somebody does a V early and then you just go through and you fall straight through, you've not checked the condition properly. Okay, so this is a problem. And then you could say, well, does this fix the problem? So I only signal if the semaphore queue is not empty. Seems closer, except you can't do that because you're not allowed to look. And so there's a race condition here right in between as well, which can screw it up. And so just to close this out since we're done for the day. It's actually possible to do this correctly. If you try to come up with a horse scheduling, you can look in the dinosaur book. They show you how to do it. Complicated but doable. I encourage you guys to think about a MESA scheduled solution because it's much simpler and doable. Okay, so in conclusion, for monitors represent the logic of the